Hey guys, Mr. Klein here, Chapter 7, Lesson 3, the theory of plate tectonics. The most important theory of all of geology, the one theory to unite them all. That important. I'm probably the only person that is excited about this at this moment, but that's okay. If you're in my class and you're watching this video, this lesson will spread over 2 days. So if you're watching this on YouTube, this is going to include plate tectonics and convection currents. Convection currents will be later on. My class, we're going to talk about that on the second day, but on the first day, we're going to go ahead and we're going to talk about plate tectonics. So let's go get going. And by the end of this lesson, you will be able to answer these 3 questions. Question number 1 is, what is the theory of plate tectonics? Question number 2 is, what are the 3 types of plate boundaries? And then question number 3 is, why do tectonic plates move? So let's go ahead and let's get going. And let's go to Google Earth. Here's my class. So let's zoom out. Okay? And we need to do some investigation, like a scientist. Now, as in our lesson, Chapter 7, Lesson 1, we talked about the continental drift theory. Alfred Wegener talked about how he was convinced because South America right here and Africa right here seemed to fit together like a puzzle, and along with other geologic clues like fossils, coal beds down here in Antarctica where it's nowhere near as cold enough to support warm enough to support coal beds, glacial fields down here, among other clues, showed that obviously the Earth's crust was moving around. And the continental drift theory only took hold in the 1960s when we had satellite footage. Because if we look at this, and exploration of the oceans, because if we look at this, we notice there's this big line running across from around Antarctica. And if you notice, it runs along the Atlantic Ocean, it cuts across, goes right here, and it runs all the way to Iceland, and then it suddenly stops. And so we see that, and then we go across the Pacific Ocean. We notice these really dark lines. These are really deep parts of the ocean. These are oceanic trenches. If we notice around Japan, it's really deep, and this line pretty much goes continuously from up here in Alaska. This really deep ocean goes up to right here in Russia, down to Japan, goes across, and then you have some deeper ones right here which go around the Philippines, and then it comes across right here, and you have really deep in right here is the Marianas Trench, the deepest part of the world. And if we notice, the line continues, and it goes around, okay, and it cuts through New Zealand, and it continues right here. And if we go and we look, same thing south of Indonesia. And so scientists are like, hey, there's something going on right here. And so whenever we looked at natural phenomenon, we also noticed something else. In fact, if we notice these deep parts and all these lines and stuff, if we were to look at where the volcanoes were at, suddenly we start seeing a correlation. There's a lot of volcanoes right here along this trench, and notice these volcanoes follow along these trench lines, and right here too. And even there's volcanoes here even in New Zealand, and we go across the western United States and we look here at Central America, we see the same deep ocean right next to the land, the continental crust. Same thing in the Andes. So something must be up with that. And even look right here around Iceland, we see a lot of that. And so whenever we correlate the volcanoes with that, we notice something's up, that this continental drift theory might be working. But then whenever we look at earthquakes over the past couple months, we start seeing a little bit of correlation. And then whenever I put on historic earthquakes, a pattern begins to emerge. If we notice all of these gray spots, how they congregate. They congregate along these lines that we saw in the ocean floor and where all the volcanoes are at. Okay, so obviously something is up, and Alfred Wegener was right. In fact, let's go ahead and let's take off the earthquakes, and let's just put the tectonic plate boundaries, and what we see is Alfred Wegener's theory essentially, for all intents and purposes, being correct. All of these lines you see are tectonic plates. They're big chunks of the Earth's crust that move across each other. Okay, there's about 14 major plates, and there's a couple other smaller ones. And so we're going to spend some time talking about this all day for this lecture. And so before we get going, this one's going to be a long one. So I'm going to give you some time. Go grab yourself a soft drink from the fridge, come on back, have a seat, and get ready. Okay? You can go. Alright, so you're back. So let's go ahead and let's get going with these notes. Question number 1 is asking, what is the plate tectonics theory? So let's go ahead and let's answer that one right now. The theory of plate tectonics states that the Earth's surface is divided into large plates of rock. Each plate moves over Earth's mantle and changes position with respect to other plates. Okay, once again, the theory of plate tectonics states that Earth's surface is divided into large plates of rock, and each plate will move over the Earth's mantle and change position with respect to other plates. Okay, so we see this in several different ways. For example, we see when plates separate across the ocean floor, mid-ocean ridges form. Like, for example, this mid-ocean ridge over the Atlantic Ocean is the process of 2 plates separating. Okay? Now, when one plate will dive underneath another plate, earthquakes result and mountains can form. Like, for example, we have the Earth's crust diving underneath here. And the Andes is geographically the largest mountain range on the Earth. And in addition, over here, the Himalaya Mountains, we have 2 plates running into each other, and these mountains are being formed. Also, earthquakes will result where plates slide past each other. Okay? If we go over here and to the United States, and we go and we look in the western United States, and I turn on real-time earthquakes, and we go and we look, especially if I put on historic earthquakes, we'll see a lot of earthquakes forming along this spot in California. Here's Los Angeles, here's San Francisco. Okay, so those are 3 types of plates which we'll get into later, but essentially that's 3 ways that plates run into each other and they move. Okay, they'll either separate, one will dive underneath the other one, or they'll slide across each other. Okay, so of all of Earth's tectonic plates, the Pacific plate is the largest. Okay, so let's look at this. This map is of all of Earth's tectonic plates. The biggest one is the Pacific plate right here. We also have the Australian, the Philippine plate. See, that's where that trench you saw right here. We have the Nazca, the Cocos, the Caribbean, the Juan de Fuca, North American, Eurasian, Arabian, African, Scotia, there's a smaller one there, the Antarctic, the Indian. Okay, so there's 14 main plates, and there's several smaller ones. And so what happens is all these plates move and bounce into each other, and that's where we get volcanoes and earthquakes and things of that nature. So let's go ahead and let's talk about this. Now, how does this happen? Well, the cold, rigid rock layer of the outermost part of the Earth, this includes the crust, both the oceanic crust, which is the more dense part of the crust, and the continental crust, which is the less dense, and the very top of the mantle. This forms what we call the lithosphere, which, like I just said, consists of the crust and the upper part of the mantle. Below the lithosphere is what we call the asthenosphere. Okay? The asthenosphere is just below the rocky part of the mantle, and it's so hot it's actually plastic. It's essentially like a freshly baked cookie where you push the top of it, and it's not liquid, but it's solid and it's kind of soft and pliable. And the asthenosphere is really important for plate tectonics because it is pliable and it's kind of starting to melt in a way. As a result, it's a smooth surface that the rocks can move on. Speaking of cookies, if you put cookie dough on an untreated piece of metal and you put it in the oven, you bake it, the cookie will bond to the metal plate, and you gotta scrape it off and you get, all sorts of junk. But if you spray some oil or use a non-stick plate, it'll slide right off. And that's essentially the function that the asthenosphere does. So, that's what the asthenosphere does in relationship with this, but also plates of the lithosphere will move because they rest on the flowing asthenosphere, which I just talked about. Okay, so that's how they move. They slide across the asthenosphere really slowly. Because remember, the asthenosphere only moves at about the speed which your fingernails grow. Now, the place where 2 plates meet are called plate boundaries, and this is some really important stuff right here. So you need to pay close attention. Okay, first type of plate: when 2 plates move away from each other, a divergent plate boundary will form. So let's hop into Google Earth. Okay, here's California. Let's zoom out. Okay. And let's go ahead and let's go look, and let me take these earthquakes off for a second, and let's look at the Earth. And what do you see? You see along these ridge lines, you see a lot of vertical mountain ranges. So essentially what's happening right here is the 2 plates are moving away from each other about 1 inch per year, okay, 2.5 centimeters if I'm not mistaken. And what's happening is as these plates move, molten rock from the asthenosphere keeps on pumping up, and that's new rock coming to the surface. And so over millions of years, these vertical lines are the result of this plate movement. Okay, so that's divergent plate boundaries. In the ocean, mid-ocean ridges are located at divergent plate boundaries. But that's not the only place where divergent plate boundaries take place. Occasionally, they'll happen within continental plates, and what we'll have is what we call a rift valley. And oftentimes, instead of mountain range and stuff, oftentimes you'll see active volcanic activity. And we'll see this in Africa. The African plate, okay, actually has some cuts through it. And this area right here, okay, from Lake Malawi through, you see this yellow line, Lake Tanganyika throughout, but next to Lake Victoria to Lake Albert, all this is what we call the Great Rift Valley. Okay, so this is a divergent plate boundary going on within a continental plate. And when we talk about fault lines and stuff, that this gets, this gets a little more complicated. But for our intents and purposes, you'll see sometimes divergent plate boundaries in the on the continents, and rift valleys will result. Now, when two plates slide by each other, a transform plate boundary will occur. And this type of movement doesn't cause volcanoes or anything like that. Rather, it causes earthquakes. Think of transform plate boundaries. Let's go to California and let's look at the San Andreas Fault. This is where the Pacific Plate and the Pacific Plate and North American Plate collide. Okay, and we'll turn on historic earthquakes for a second. But think of it as like a cracker, a graham cracker. Now, graham crackers will cut along those indentations. Okay, so let's break a graham cracker apart. And now we're holding this one piece of the graham cracker, and let's break it the opposite way. Not around those borders where they're cut, but rather in the middle. So you've broken it in half, and let's put it back together. Okay, now slide them across each other, and what happens? Okay, yeah, that's what happens. You notice it kind of catches, and it moves, and then it like kind of cracks, and you get crumbs all over the place. That's essentially what a transform boundary is doing, is that these rough lines on the San Andreas Fault will catch, and so you'll have a lot of potential energy form, and then they'll suddenly release, and it releases a lot of energy in the form of the earthquake. Okay, and so that's what happened right here. Okay, in 1989, on October 18th, 1989, in Northern California. Your parents, or even if you have an older brother or sister who's in their late 20s, will probably remember this. I remember this. I was 7, almost 8. In fact, it was almost my 8th birthday. This should tell you how old I am. But it was the World Series, Game 3. The Oakland A's against the San Francisco Giants. And just minutes before Game 3 started, we were all watching on TV, and suddenly it goes black, and it's shaking and stuff, and it was a huge earthquake, and there was a lot of damage in San Francisco. Lots of people were killed. Okay, the World Series had to be postponed for a while, but that was the result of that friction and the release of energy along a transform fault, a transform plate boundary. Okay, so transform plate boundaries, you'll see a lot of earthquakes. Divergent plate boundaries, you'll sometimes see them, but oftentimes you'll see volcanic activity, which if you saw in Africa, they had several volcanoes there. Okay, so let's talk about the other type of plate boundary. Okay, and the two types of that one general idea of plate boundary. When two plates collide, we have what's called a convergent plate boundary. Okay, which will form. So when plates collide, the plate that is denser, and which we know that the two types of plates are oceanic and continental. Guess which one's more dense? Yes, the ocean plate. The oceanic crust was always denser because they got water sitting on top of it, and it pushes and makes it more dense. Okay, so when plates collide, the oceanic plates will slide under the less dense plate through a process which we call subduction. Subduction being meaning going under, so it's being pushed underneath the plate. Okay, and lots of things happen right here. We have earthquakes, we have volcanoes, and we have mountains that form here. So what will happen is when an oceanic plate will slide underneath a continental plate, a deep ocean trench will form. And near the trench, a line of volcanoes will form. Okay, so let's go ahead and let's look at this. Japan is the best example, and actually this is what we saw at the very beginning. Okay, so you see all these earthquakes and all these volcanoes. I'm going to turn off earthquakes for a second. Let's keep the volcanoes up, and let's look at the tectonic boundaries. Okay, so along this line you see the trench. The Pacific plates here, okay, North American plates here. Okay, the volcanoes form right across here because it's pushing under, and the oceanic crust is melting, which forms a lot of magma, which can then push up through heat because remember, heated things rise and it pushes up through the surface. So we go here, okay, and notice right here in Russia, where there's a lot of plate movement and stuff right here, okay, you have a lot of volcanoes, and there's this trench that follows along, and here's Japan. Okay, so here is a continental plate right here. Here is a oceanic plate. This oceanic plate is pushing under. This one's pushing at a pretty fast rate. 92 millimeters per year, 9.2 centimeters, okay? That's a couple inches, you know. That's a lot for the movement of the Earth, okay? And so when we have two oceanic plates that will collide, we have this, okay? We have volcanoes, they form, and they'll often form in a band like this. So you see this, okay? So this is where the Pacific plate meets the Philippine plate. And this isn't the only example of it. And see, here's where a continental plate meets an oceanic plate also. Here in Indonesia, all these volcanoes. Okay, so if we go and look, we'll also see mountains form. Like here in New Zealand, okay? Here's a bunch of volcanoes here, and there's a mountain range here. But the big example is here in South America. In South America, we have a lot of, where it's pushing in a lot, we see a lot of volcanoes right here and right here. But in addition, you have the Andes Mountains, okay? The longest, remember, the longest chain of mountains in the world. These are being pushed up because of the subduction going on, okay? So, and this also, the oceanic will also happen right here in the Caribbean Sea, okay? So you see the mountainous of Haiti and the Dominican Republic, a little bit of Cuba, and then the volcanoes form where they're colliding and they're pushing into at a really slow rate, 18 millimeters per year, in the Caribbean Sea. So let's hop on back and let's talk about the second type of boundary, okay, of convergent plate boundary. Okay, and as you saw, an island arc forms because two oceanic plates collide. Now, when two continental plates will collide, neither plate is subducted and mountains form because neither one is appreciably denser than the other one. And the best example we have of that is over here where the Indian subcontinent is colliding with the Eurasian plate at 48 millimeters per year. Okay, and you have the Himalaya mountains forming right here. Okay, here is Mount Everest. Mount Everest, tallest mountain in the world. Okay, 48 meters, 29,028 feet. Okay, it's so high it actually reaches the jet stream. Okay, so these mountains right here are a result of the Indian plate running into the Eurasian plate, and they're pushing up against each other, and they're forming mountains. Let's head on back to our notes. Okay, so the convergent plate boundary, there's two types. There's where the oceanic plate meets the continental plate. Okay, the more dense of the two gets pushed down. Okay, we have volcanoes that form as a result. Also, it pushing down produces mountains like the Andes. Okay, and then whenever you have two continental plates running into each other, mountain ranges will form as a result of that. Okay, and so let's watch motion at plate boundaries for you can see the animation. Okay, so here is a divergent plate boundary. Okay, so we have new magma coming up from the hole where it's being pushed away, and you're going to have volcanic eruptions and earthquakes. So let's hit play, and notice you have volcanic eruptions, new lava comes out, and occasionally you'll have an earthquake where the rocks are jarred and they're moving away from each other. So here's a convergent boundary, okay? Or rather, let's go to a transform boundary, just like I went with in the order in our lecture we were just talking about. Okay, they're going to slide across each other. Note, there's no volcanoes. So we'll hit play, and these mountain ranges are slowly moving away from each other, and as energy is released from it catching, you see earthquakes take place. Finally, the convergent boundaries. Here's an oceanic. Okay, so we hit play. This plate's being pushed under because it's more dense, and as it melts, it creates a magma hotspot, which creates volcanoes, and you have your island arc right here. So here's how it all fits together. Okay, and as the further away you get away from the mid-ocean ridge, it's the older the rock. So let me hit play, and let's go over to tens of thousands of years. Okay, we have subduction going on right here. Okay, and it's folding under, creating mountains. Okay, so you have your volcanoes here, and so let's hit play again. Okay, you have volcanoes and you have earthquakes here. You have earthquakes right here. All these volcanoes and earthquakes, which we'll talk about later in the school year, are occurring at these plate boundaries. Okay, so here's a summary. Here's a little cheat sheet, the interaction of tectonic plates, just to review one more time. This is how important this is. First off, divergent plates. They're spreading apart. Okay, notice right here in the picture, they're spreading away from each other. The mid-ocean ridge in the Atlantic Ocean is a good example of this. Transform plates, they're sliding across from each other. Okay, they're sliding across, they're catching, causing earthquake. The San Andreas Fault in California is an example of this. You have conversion, or ocean-to-continent plates. Okay, they're colliding. The more dense of the two is slipping under. Good examples of this is Japan colliding with the Pacific Ocean, in Indonesia colliding with the Indian Ocean, also Haiti in the Caribbean Sea. And then we have continent to continent colliding where mountains will form, and that's the Himalayas. So how does this happen? Well, we'll get to that in a second. So, evidence for plate tectonics. Scientists now use satellites. I mean, without satellites, we wouldn't have Google Earth, and I couldn't show all that information to you, to measure how continents move. The theory of plate tectonics will explain why volcanoes and earthquakes occur in certain locations. Because if you saw at the beginning of this video, the correlation between the two. At the tectonic boundaries, we have lots of earthquakes, and we have also lots of volcanoes. Okay, but we don't always have earthquakes at those. Sometimes we'll have them in different spots. When we talk about earthquakes, we'll talk about that later. So, but why does this happen? I mean, what's causing all the movement to take place? Okay, so this is where my second lesson is going to start. So if you're just looking for information about plate tectonics and the actual movement, here's a good time to stop. But if you want to find out on the why, especially if you're in my class and this lesson goes on for 2 minutes, goes on for 2 lessons, here's where we're going. Why does this happen? Well, the Earth's mantle moves because warmer, less dense material rises and cooler, dense materials sink. Okay? And materials will move based on differences in their temperatures and different densities in the process of what we call convection. Remember, there's 3 types of heat transfer. There's conduction, where something touches something else and heat is transferred. There's radiation, where you don't need to touch. Okay, the infrared, the heat waves, the electromagnetic waves will move through a vacuum. That's how we get it from the sun, warmth from the sun. Then we have convection, where molecules move because of the movement of the heat. Okay, so inside the Earth, we have radioactive elements provide some of the thermal energy that causes convection. The other is like friction and pressure. But radioactive, what will happen is subatomic particles will leave an atom. And as a result, heat is generated through that decay. So that, along with the pressure and the movement of the outer core, the friction of the outer core hitting the inner core and the mantle, causes heat. And heat always rises. So it radiates out from, it convects out from the core out toward the mantle. Okay, and from the mantle out to the crust. So convection currents will form in the mantle when the thermal energy transfers, like I just said, from the core to the mantle. Okay? So what that then happens is it actually moves the plates themselves, which I'll get to in a second. I'm going to skip over that picture and come back to it. So what will happen is we have 3 forces interacting to cause tectonic plate motion, according to scientists right now. Number 1, convection currents in the mantle produce a force that causes motion on the whole plate itself. They're what we call basal drag. Basal meaning the base. So the base of the plate moves as a result of this. It's being dragged across. Now, when plates are pushing away from each other at divergent boundaries, we have a force that's causing this at what we call ridge push. Okay? So on the ridge push, what we have is it gets really hot and it gets up there, and the heat is pushing the plates away from each other. And as it cools off, basal drag will then drag the rest of the plate off. But what about where subduction? Why is it being pulled under? Well, what happens is the asthenosphere is kind of cooling off in this place, and so the mantle's touching and it's kind of bonding. And as the convection pulls, cooler air starts sinking, going down toward the core, the plates are being pulled back down. And this force that pulls it down is what we call slab pull. Okay, so let's look at the picture, or you can see mantle convection in action. So we have radiation, we have friction, we have all pressure, all that generating heat, and it gets pushed up, and it goes through the mantle. It gets to the top of the asthenosphere, and here at the mid-ocean ridge is where we have ridge push. Okay, so the heat pushes them away from each other. Okay, and so that's why hot magma pops up from there. And so the heat, once it reaches the cool crust, it'll start cooling down, and it'll bounce off and start moving across. And as it moves across, that's where you get basal drag. And so that's moving the plate away from the divergent plate boundary toward the convergent plate boundary. And it cools off enough that the density is thick enough to start sinking. It pulls down the tectonic plate with it, and so that's where rather we have slab pull, pulling it underneath it. Okay, and actually with sensitive instruments, scientists have been actually see huge chunks of rock in a mantle where we see slab pool, and then we see huge chunks of molten rock coming up. Okay, the heat, we see these convection currents coming up, going to cause the ridge push. Okay, so that's mantle convection. Okay, remember, ridge push, basal drag, slab pull. Okay, so to start wrapping things up, plate tectonics, like I just said at the beginning of this, is the unifying theory of geology. Okay, everything from mineral creation to earthquakes revolves around plate tectonics. It all makes sense. Everything makes sense with plate tectonics. Now, plate tectonics is an accepted theory, is only 60 years old, and with more sensitive instruments and better improved techniques of observation, what's happening is the plate tectonics theory is still being revised as scientists learn more about plate tectonics move. Okay, for example, scientists are still arguing over which one of these three forces, basal drag, ridge push, and slab pull, will cause it. When I was in high school, they were saying that basal drag was the main cause of plate tectonic movement, but research since my high school days has said that maybe ridge push and slab pull work together, and basal drag is just what happens as a result. So science is still moving. This is a scientific method in progress. Okay, we have new observations that help explain things better, and theories are revised as a result of that. So, long lesson, I know, a lot of information, but remember, the big things are the three forces you just saw, and then the plate boundaries. So, let's answer these questions. What is the theory of plate tectonics? Well, the theory of plate tectonics states that the Earth's surface is divided into plates of rock, and these plates move across the mantle, changing position in respect to each other. Once again, plate tectonics, the theory states that Earth's surface is divided into plates of rock, and these plates move across the mantle, changing positions in respect to each other. Now, what are the three types of plate boundaries? Well, of course, there's three. There's separating, which is a divergent plate boundary. There's a transform boundary sliding across, like right here, down here is the San Andreas Fault. That's the transform plate boundary. And then whenever they come together, that's a convergent plate boundary. So why do they move? Okay, here's why. Tectonic plates move because of convection, or the heat currents moving through the mantle. As heat from the core reaches the asthenosphere, that's that plastic layer near the top of the mantle, plates move due to basal drag. They're dragged across by the heat, okay, the bulk of the plate. At divergent plate boundaries, where they separate, this heat will cause ridge push. They push away from each other. And at convergent boundaries, where it cools off and it becomes more dense and starts getting sucked down into the mantle, the crust is pulled down due to slab pull. So, there you go. There's the three answers to these questions, the three big important things. Once again, any questions for my students in my class, feel free to let me know. Anyone online have any comments or things like that, please feel free to let me know. If you flame it, I'm just going to ignore you. Anyway, constructive criticism, of course, is always welcome. So until next time, talk to you later.